An array is a variable that can hold more than one value. But how does MATLAB know that we're creating an array versus a regular variable? Now there are very few symbols to know, just a hard code arrays. Now the methods shown here are just for small arrays, for 5, 6, 10 values. But as soon as you're going to have big arrays, this is not the way to go. So this is just to get started into using the symbols that you need. Square brackets, semicolon, apostrophe, comma, and colon. Square brackets is basically what MATLAB's going to look for in order to know this is an array versus a regular variable that can hold one number. Commas are optional, but they're there to separate columns. So numbers, if your example we have 5 numbers and they're separated by a comma, MATLAB will realize these numbers are in different columns each time. Instead of commas though, we can just put a space. That will be sufficient. Semicolons are necessary if you want to create a row. So if you want to create multiple rows, each time you want a new row, we will put a semicolon. This is necessary for column vectors. It's necessary for 2D, 3D, 4D matrices. The apostrophe is kind of a lazy way. If you have a column vector and all of a sudden it needs to become a row, or you have a row vector and it needs to be a column, or you have an array and you want to flip it, so rows become columns and so on. The apostrophe is there to transpose, and that's exactly what transpose means in mathematics. You're flipping the array. Colons are useful when the values have an addition pattern. Basically, for example, 2, 4, 6, 8, 10. Well, there is an interval of 2 between each value. And instead of typing 2, 4, 6, 8, 10, there's actually a much quicker way with the colon. So we're going to see about 3 examples just to practice the symbols. The first example deals with physics. The work is the amount of energy transferred to a body by a force acting through a distance. So, for example, a man pulling an object. He's going in a direction, x, y, z, 3-dimensional, and he's using a force to pull the object behind him. So the force is also in the xyz direction. Notice how these 2 words, or these 2 letters, have an arrow on top. This is one way of representing that it's a vector versus just one number. The actual work done on the object is simply calculated using the formula F dot product D. So the dot product between the force and the distance vector. In order to apply that though, you need 2 vectors. You need the force in the xyz direction, and you need the distance in the xyz direction. Now notice how these are 2 column vectors. They're 1 column each. So we're going to go in MATLAB and create those. As far as the algorithm is concerned, it's pretty straightforward. Define the force and the distance, vectors, and then calculate the work. So the force was a column vector. Square bracket 9. Since it's a column, I need a new row. 12.3, new row, and 3. Now when we run, MATLAB actually shows it as a column vector. This is one nice thing. It shows exactly the way it is on our paper. Now the semicolon was used to separate a row, but keep in mind that from the beginning of the semester it was also used to suppress the output. The distance vector was also a column vector, but I'm getting tired of doing semicolons, so I'm going to use the lazy method of the apostrophe. I'm going to create a row vector, and notice how I've just used 1 space or 2 space or 3. As long as you have white space, MATLAB understands that they are a new column. This is a new column. Now when I run, notice how it's not a column vector. So I can ask to transpose just by doing the apostrophe. Now the distance vector is back to being a column vector. So you can choose to put the semicolon in between each number, or just wait until the end and put the apostrophe. Again, I will hide my output. The work is nothing but the dot product between the force and the distance. Now we are lucky enough that MATLAB has a dot product, a dot function ready to go. The result is 119.7. The unit is joules. So this is a very brief introduction to vectors. Semicolons, brackets, and apostrophe if you're lazy and don't want to put semicolon between each value. That concludes the first example. Example 2 also deals with physics. The Lorentz magnetic force is the force on a charged particle due to an electromagnetic field. Charged particle, what is it? Well, electrons and protons are charged particles. And an electromagnetic field. Imagine you have a magnet, there's an electromagnetic field. Just like electromagnetic fields attract metal, they also attract electrons and protons. Now, one application of this interaction between the two is to change the direction of a particle. Suppose you have an electron that's traveling along the x-axis with a certain velocity. If there is no magnet, nothing happens. But as soon as you have a magnetic field, and that's the B vector right here, the electron tends to shift direction. It's no longer going to follow the x-axis. Why? Because we have a force. It's called the Lorentz magnetic force. And it's nothing but Q times V cross B. V is velocity, B is magnetic field, and the cross is the cross product. It's not multiplication, be careful. Q is the charge of the particle, and that's something that we can Google periodic table, find anything that we want. This is easily found. So, for example, if we apply it to our electron, the charge of an electron, if you Google, is negative 1.6 times 10 to the negative 19, and the unit is coulombs. Now let's suppose that the velocity is 3 millionths in the x direction, so our electron is going really fast in the x direction only. 0 in the y direction and 0 in the z direction. Let's also suppose that the magnetic field is very, very small and only in the y direction. 3.3 times 10 to negative 3. First question, what is the force exerted on the electron? We're going to use the equation at the very top. And then what direction does it go to? If you notice the F, it actually has an arrow on top, which means it's actually a vector as well. So we're going to have an X, a Y, and a Z component as well. So it'll be very easy to tell which direction the electron goes to. Now again, the algorithm is straightforward. We just need a couple givens and one equation to the end. So the charge of the electron was negative 1.6 e negative 19 coulombs. The magnetic field was a vector, so we do use brackets, and it was 0 in the x direction, very small in the y direction, and 0 in the z direction. Unit Tesla. Velocity was very big in the x direction, but nothing on the y, nothing on the z. Now, since I put my semicolons, I don't see any result at the bottom, but running shows me what I have in the workspace. I can see I have 3 variables, and notice how MATLAB still shows the same idea of vectors. Brackets. To calculate the force is the charge times the cross product of the velocity by the magnetic field. Run. The force is very small. When you see that kind of thing, MATLAB is saying that there's a common factor in all numbers. In those x direction, it's 0 times 10 to the negative 14. So that's still 0. Same for y, but for the z direction, and that's where the force is pulling the electron towards, there's a very small force, negative 0.15 times 10 to the negative 14. Now if we think about it, it's a small, small, small force. But let's calculate the acceleration. F equals m times a. Acceleration is the force divided by the mass of an electron, which, if we Google electron mass, it's something that we can just copy, paste, and make sure we do times 10 to the negative 31 MATLAB's way. So when I run this, MATLAB actually shows an acceleration on the electron of 1 times 10 to the power of 15 times minus 1.7. The negative simply indicates in the negative z direction. But this is a huge force. Now, how could we use this in the real world? Why is this an actual really cool equation? Well, what if we added an electric force? The equation doesn't change much. There's an E, electric field, and we already know that the magnetic force changes the direction. It creates a force, so it pulls the electrons somewhere else. Well, the electric force adds a velocity factor. It changes the velocity of the particle. So the perfect application for this is a thrust by magnetic field, and this is currently researched. It's currently researched because there are a couple drawbacks, and if you can Google if you want to. But MPD, magnetoplasma dynamic thruster, is basically counting on the magnetic field to push the propellant in the correct direction, and the electric field to speed up the propellant, so to create a thrust. So if this tiny equation can be used on one little electron, imagine how much force can be created to 1,000,000 of those. So that's really a cool example. Last example, but this time with matrices. System of linear equations. This is something that most of us have solved at least once, and the most common method is substitution. For example, we take equation 2, and we actually solve for y analytically. So y is a function of x. Once we know that, we plug it back in to equation 1, so we substitute it into 1. We only have one unknown, which is x. It's very easy to solve. Once we have x, substitute it into one of the equation and solve numerically for y. So finally we have x equals negative 15, y equals negative 27. Now mathematically, and specifically for MATLAB, if you remember, MATLAB is matrix laboratory. MATLAB loves this kind of things, loves matrices. So in vector notation, it would be a times x equals b. A is the matrix of coefficient for x and y. Notice the order is identical to your system above. X is the actual vector of unknowns, x, y, z, t if you have more. And b is the coefficient on the right-hand side, 9 and 12. Now to get rid of a, we can't just divide b by a. This would be normal math, but this is matrix math. So we simply need to multiply on the left side by the inverse of matrix A. That's matrix math, just accept it. Now again, very short problem to set up. We have two variables. Variable A is a matrix, brackets. We respect the order that we have on our system. Run, just to quickly see what it is. If you're happy, put a semicolon. B equals, and I can either do 9 semicolon 12, that will create my vector B, or I could have done 9, 12, and be lazy with the apostrophe. Both methods actually work. I'm going to hide the output. Okay, and to solve for my x and y, so my solutions, I would have the inverse of A times B. When I run, I gladly, happily get the same result that I did with the substitution method. It is in the same order as my x on paper. So the first number was x, negative 15. The second number was y, negative 27. Now there's actually another method, and this is only because MATLAB is matrix oriented. MATLAB has created some shortcuts. A left divide B. Notice this is not the division symbol. If I did 2 divided by 3, it's that slash. But if I do 2 backslash 3, then MATLAB reads it the opposite way and divides 3 by 2. So in matrix math, this is possible. And that concludes our little substitution problem. Very quick to do. Don't hesitate to use MATLAB to check your math homework. It's very quick and you get an instant result. That concludes our matrix. Now the last symbol that I want to introduce, but I'm not going to do an example, is the actual colon operator. We've somewhat used it before in the for loop, but here we're simply going to use it to create an array. There is no bracket. They're useless. MATLAB doesn't need them at this point. The colon is identical to the for loop. It meant go from one number to another by increments of something. Well, 1:4 means go from 1 to 4 by increments of 1. We can introduce an increment, and it can be a decimal. And notice how quick MATLAB creates a row vector. It has 1, 2, 3, 4, 5, 6, 7 elements. We can go backwards too. As long as we put that increment in the middle, MATLAB will be happy to count for us. It's much quicker than actually hard coding 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And if you forget symbols, you gotta fix them. So notice how there's less coding and MATLAB does the job for us. This example is mostly used for plotting, so we'll get back to it in future tutorials. Now finally, just know that you can combine any method that we're showing you. If you want to create an array that has the number 1, 2, 3 on the top and goes from 10 by -1 to 8, you can do it. So you can combine the semicolons, the brackets, the colon. The only rule that you need to respect, and actually it's pure common sense, is it has to be rectangular. Don't try to create something that doesn't have the same amount of numbers in each row and each column. This is the error message that you will get. Vertical concatenation. Concatenation means to glue together. So you're trying to glue pieces together vertically and the dimensions are not consistent. So as long as you respect the rectangular aspect, you can combine any kind of method that we just showed. Alright, this concludes hard-coding arrays. Here's a couple credits, especially if you want to do a little bit more research on the MPD thruster. As far as lessons learned, not many symbols, but they are important. Brackets tell MATLAB this variable can contain more than one value. Commas, semicolon, colon, and apostrophes. Now remember, those symbols are for small vectors, small matrices. As long as it's big, this is not the way we're going to go. We're going to learn much better methods. The colon is technically the exception because you can create big arrays in very little coding. Start, stop, increment. Combine any symbols as long as the array created is rectangular. And go ahead, do try to use MATLAB as much as you can to check your math homework. This concludes this tutorial.